as laminations. So the purpose is to minimize or reduce or decrease eddy current losses.
Yes,
okay?
Yes, as Dr. Muhammad Khalid said, these are sheets and they are laminated. And each sheet and other sheet is isolated from each other electrically because this is basically a conductor. This is iron. Iron is not the perfect conductor, but it is very good magnetic material. So these sheets are insulated from each other to reduce the eddy current, as Dr. Muhammad Khalid said, that when we have flux here, when we have varying change in magnetic field and change in magnetic flux, it will generate currents in this way. If we have flux like this, it will generate currents from the right-hand rule. So these currents generated, if we laminate these sheets, this current will be reduced. This is the losses that we want, the eddy current losses that will be, because this is a conductor and there will be internal currents generated which will be converted later to heat.
Also, you can see that how this flux is generated. You can see that these two wires are the input. This is power supply. So when you apply a voltage source, this is the coil. Lot of wires are wound like this inside. And once the current is passing through this coil, a magnetic field is produced around it. You know this first principle in electrical. Whenever there is a current passing through the coil, a magnetic field is produced. This magnetic field is basically flux. And this flux is basically transported from this part of this material to here. So it goes like this inside this core, okay? And if I want to make a transformer, let's say this is primary side, and I can make another coil similar type like this. I can make another setup like this here, and I can take out the voltage which is secondary voltage. It becomes a transformer. Clear? So this voltage source is basically creating a current passing through this coil. It produces a flux around it. This flux is transported to this coil, so this core basically. And if I want to make a transformer, I can make this type of coil here, and that coil can bring the current from primary to secondary without any physical wire connection. It is through flux, which is electromagnetic induction.
Yes.
Okay, because there is no physical electrical current passing through this core. Only flux is passing.
Yes.
Okay, so this is one application.
And the primary and secondary will be magnetically coupled.
Yes.
And you can transfer the power through the magnetic circuit here. Okay. And we will see later in the transformer experiment that we can have different voltage here and here because the number of turn will affect. For Faraday's law, if you have one number of turn, you have some flux, change in flux. If you have one number of turn, you will have specific voltage. If you have two, you expect double. If you have three, you expect triple. So this is how you will change the amount of voltage induced in the primary and secondary coil. So this is basically our magnetic circuit. So in our lab, we will connect this to a variable AC power supply. When we connect it to a variable, so we have here variable AC power supply. We will use line 1 to neutral. So this is our variable AC power supply. And then we will use, of course, we will connect first the power supply to the fuse, then it will come here. But before it comes here, we will measure the voltage and the current in the isolation amplifier, Cassi sensor, as we usually do. We will then do the Cassi lab setting. Then we will do our experiment, which is basically increasing the voltage and taking measurements at different voltage levels, and the current will be changing also. So this is basically an introduction to the equipment and the experiment today. Okay, so now we will follow the procedure. We will do the experiment. In the procedure, we have here variable AC power supply, as we said, and then this variable AC power supply. We will measure first the current here from this channel B in the isolation amplifier, and then this will go to the Profi Cassi, and this is 1 volt per ampere. And the same, we are going to measure the voltage here in the channel A, UA with OA. We are measuring the voltage and current. So then it will go to the coil. This is basically our magnetic circuit and the coil. So
the first thing is power supply.
Yeah, so the first thing is the power supply. We will start from the power supply. So now I will bring the wires. So now you have here the positive terminal of the power supply. Basically, this is sinusoidal. It is
this is single phase AC power supply.
This is single phase AC power supply. Yes. So this will go first to the fuse.
To the fuse.
Before going anywhere, it will go to the fuse. So after the fuse, we will measure the voltage and current. So after the fuse here, we are measuring the current here using channel B, and from there, and also we are taking this for voltmeter, because voltmeter is open circuit. There will be no current, very small current coming here just to measure the voltage. You can assume this is 0. This is no current here, but this is coming to the ammeter, and from here it will come back. From the ammeter, it will come back to our device, this one. So we are connecting this terminal here. So this is the positive terminal. Yeah, basically it is sinusoidal, positive and negative are interchanging.
Just like this.
But it is better that we stick to a specific conversion. So now we do the other side. So this is the positive side. This is the neutral for the AC. This neutral we are giving, we are connecting to the power supply. Then we come to the isolation amplifier. We connect it to here to measure the voltage. So this is voltage. Sorry, to measure the voltage we have to put it here. So this is voltage from here to here, and this is for the current. And we will make this over 100 for the voltage, and this is 1 volt per ampere, as we usually do, 1 volt per ampere. And this is over the number over 100 for voltage. So this we will measure voltage, and here we will measure the current.
This is always true. Voltage always 1 over 100. Current is always, in our experiments, 1 over 1.
Yes. So now I will, from the same node I can take again to connect it here. So I will connect to the negative. I can connect either here or there. They are the same node. So
which is like this. You can see from here. So this one you can quickly see from here.
So now this is our connection. So as you can see, we have the AC, variable AC power supply. First it goes to the fuse, it goes to the isolation amplifier and come back here. Now we want to send this data to the sensor. So from here the voltage will come from here to here, and the current will come from here to here. So this is UA1, UB1. UA1 will represent for us voltage now, and UB1 will be current. So now let us connect this. So this is UA1 and UB1, and this is the common. So these three is coming to the sensor because we will later on display it on the PC. We will do the CASI lab setting. Okay. So as you can see, everything is ready. Our goal here, what we are measuring voltage and current. From voltage and current we will get the magnetic, the permeability, the reluctance versus intensity, the permeability versus intensity, the flux density versus intensity, B versus H, mu R versus H, and I versus reluctance versus H. So we will do all this. How we will do this? Because we assume that our frequency is 60 Hertz in our formulas when we verify them. Frequency is fixed, the waveform is sinusoidal, and we are making some assumptions to be able to use these formulas in our experiment. So only from voltage and current we will determine this quantity.
Okay, can I add one thing?
Yes.
So here in your experiment you need the length of the core. In some expressions and formulae you need the length of the core, you need area of the core, and you need number of turns in this coil. So these data is provided, it is written here. You can see here that the length of the core, which is mean length, which is 40 centimeter. We can verify with a meter here, and also number of turns which are here in the coil 400, and also the area of this is cross-sectional area of this, for example this area. So for example this side, you can see, let me make it easier for you. So here you can see this is cross-sectional. So
this is full. Yes, without this, assuming it's full.
Yes, full. So this is cross-section area, and how you calculate the length? You just if you have a meter, small meter, so you can start measuring from here and go here and then come here, and in centimeters this whole distance is basically 40 centimeter. Okay, so this L, N, A, these things are used
from here.
N from here, obviously N is the number of coils from here also. So you can see it's also written 400, and it means that this coil, this circular thing, basically there are 400 turns which are wrapped around the here. Okay, so I think it's finished. Experimental setup and information is finished.
Yes, so now we have our experimental setup, and
now we'll go for CASI settings and take the data. Okay.
Yeah, next we will do the CASI lab setting and we will start acquiring the data.
Okay, thank you.
Okay, now we have the connection ready. Now we will do the CASI lab setting because we want to measure these quantities in the CASI lab.
So let me ask question to them. How many channels we need now? 2. One is for voltage and one is for current. Only 2 channel activation. UA1 you can see here from here. If you're doing experiment, from experiment you can judge how many channel we are using. So here this channel not used, this channel not used, only 2 channels, UA1 and UB1, which is top left hand side corners of this block. You can see here. Can you please click on the top one there? See, so activation AC or DC? AC. This is AC. So RMS. Finish.
So this is and this is UA1, as Dr. Muhammad Khalid said. It shows here as UA1.
Similar UB1.
And this is UB1.
RMS,
because AC, as Doctor said, and we have UB1 for this one. So now we activated both channels, UA1 and UB1, and we have to activate whatever we are using there in the connection. So we need only these 2 channels. Now, what is the UA1 connected to? Now we are measuring, we are taking measurements in UA1, UB2. UA1 is coming from where? Just a reminder to show you. This is UA1. This is the coming to measure for us the voltage, isn't it? This is voltage, representing voltage.
Scale, we can see 100.
We divide by 100, and it is coming here to UA1. So basically, we can say here, we can define quantities, we call it voltage. And what will be the formula? UA1 times 100. So let's call it here V phase, and let's unit volts. Let's say up to 180 volts. So this is settings, and from 0 to 100. This is just for the scale, and this is the unit and so on. So we are done with the voltage. Now
Current.
we will define current. So where is the current? We will see it here. So this one is UB1. So UB1 is measuring for us what? It is measuring for us current, and it is 1 volt per ampere. It means for each 1 ampere passing, it will give us 1 volt. This device. So the current is basically the same value of the channel. So here in the formula we will call it UB1. Symbol will be I phase. In amps we expect small currents, maybe 1, or we will see. And let's take 4 decimal places because we have only small numbers, so we want to show the number. So now we define 2 things here. If you click here, you can go back to voltage, you can see the current. We define these 2 quantities. Now we want to display. On the display, it asks us here to select, I think, x-axis as display. Select I as x-axis and E voltage as y-axis. So the current is the x-axis and the voltage is y-axis. You will see later. Yani why we selected like this. You will do something at home which will be related to this. So x-axis is current, and this is basically the voltage. And we will turn off the other channels. We have x-axis and y-axis. So this is voltage versus current. We are drawing voltage versus current. So now we will close this. Now these are raw data as we did before, UA1, UB1. We don't need this raw data. We will close this. Instead of that, we need the quantities that we defined. So we have a V phase and I phase. As you can see, we have the significant figures. We have here 1 decimal, here we have 4 decimals, according to our setting.
Can I add one thing here?
Yes.
For V phase, the manual is using E, capital E. So
Yes.
this V phase is basically capital E in your
manual.
in your manual.
Do we change it here a bit?
It's better.
Yeah. So now
we change
I
it
will
back.
just change this
The
VB
name, yeah.
because here I called it VB, but actually this is just to avoid you being confused and make it easier for you. We will just make this the voltage E. The symbol we will change it E.
Current I only.
And the current is only I without.
Obviously, if you see the power supply, this is phase current, but here, so I and E is enough.
Yeah.
Just to make
and from electromotive because we are dealing with magnetic circuits, so they use the symbol E as electromotive force, but it is voltage, and I for the current. So here E, I. So we are drawing E versus I.
You can see here in the table. So EI, you need E and I only to complete this table, because H, B, mu R and this R can be determined from this formula. Everything can be determined from formula, and you need volt E, I, and some information from the first part, which is L, A, and also number of turns, and also from those formulae which are written here in the manual. You can find H, you can find B, you can find mu R, you can find R. Very simple. But only in this experiment we need what? E and I. We change E, you record I, and rest is just calculations. Okay.
Yeah.
So you have to complete this table and plot few things which are mentioned in your lab, basically here.
Same page.
Lab instructions.
Yeah, this is
Oh, just here it's written. You plot E versus B and B versus H, mu R versus H, and simply R versus H. So from this table you can plot anything you want, which is written in the instructions. Okay. So now we take the readings.
Yeah.
Okay?
So now we have our Castle Lab setting is ready. You can see here in the table we have I and E. Okay. So now we will start taking the measurements. I will turn on the power supply first. Now it is at 0 volts. I will take one measurement now from 0 to 160. In the lab manual it says increase the voltage from 0 to 160 volts in 10 to 15 steps. So I will start from 0. I will take one measurement. So what we selected here, we selected manual recording. It is now automatic. I will make it manual. So manual recording, it means I will take measurements every time one measurement. So now everything is 0. I will press F9. You can see this is our first recording. Now I will start increasing the voltage. For example, now it is يعني let's say every 10-15 volts we will take measurement here. Now I am taking F9. I am increasing I will increase the voltage. So now I am increasing to 20, taking measurement, increasing it for example to 30, taking measurement. We are going to go up to 160. So you can see the characteristics. So now at 80 volts, taking.
Just a brief vibration.
Yeah, because there is
Just a vibration.
yeah, there is
Let me hold it. Just a vibration.
yeah. So I will just remove the last measurement. There was because
So it was just vibration.
yeah. So I will just remove the last point because it is not closed, not tied together very well. So it become like this. So now we will take a measurement now again. So I think there is let me make it 100 volts. Yeah, I think because the magnetic flux of the core is changed now. Unfortunately, because it moved, there are two moving parts. So the part that moved, it changed a little bit.
Yes,
so you can see the characteristic. We will just repeat this again now. No problem. We will delete. What happened now? Because there are two parts that are not coupled very well. When there was magnetic flux moving, the part moved a little bit. So it changed the characteristic of the core. Therefore, you saw the plot behave differently. But now we will repeat the steps again. We will go back to 0.
I'll hold it properly.
So yeah, Dr. Muhammad Khalid will hold it. So the two parts will not move away from each other. Now everything is 0. I will take one measurement and I will do the same. I will start increasing the voltage and taking the measurements. So we will go up to 160 volts.
No, very smooth graph.
Yes. So now it is the device is being told. So now we will get very good graph. So now I will show the extra points that are missing here. So now I will go back to 0. So now as you can see, this is the plot, and as you can see, it is saturating after some time. Why? Because usually in magnetic circuits, the limit when you give much more flux to the magnetic circuit, it will saturate. What does that mean? Even if you increase the current in the coil, you don't get more flux, because the magnetic circuit, you can look at it as the magnetic circuit being filled. Similar to the electric circuit, if you overrate, if you put more current into a conductor, the conductor will start to melt and it will become open circuit. So this is what's happening in the electric circuit. It cannot handle a specific amount. In magnetic circuit, this will not happen. But what will happen basically, even if you increase the current here, even if you increase the current, the flux will increase. After some time, even you will reach the saturation, where you still increasing the current, you cannot get more flux because this core cannot handle much higher flux here. So this is what you see. So this is basically E versus I, and this is the characteristics. And you will determine all the other quantities from this in your lab report. So
this is the lab report part.
So this is basically the lab report parts.
You only need E and I to calculate all of these, H, B, mu, R, and R, and then you can plot based on these instructions. And some data is given on the front page of this experiment, like some data parameters like L, N, let's see here. So you need all this information, and if you are looking for theory, you can see the theoretical part is also written in this lab manual. So I think that ends this experiment.
Yes, so we are done with this experiment 3, and this is the plot that you need. I will save this file and we will send it to you to do the report.
Okay, thank you.
Okay, thank you. any question يا شباب؟ any question؟